Even though many rate laws look the same or are written the same, we know that reactions do not all happen at the same rate. And so let's talk about different factors affecting reaction rates. So the first factor that can affect the reaction rate is the number of reacting species. For example, do we have the reaction of A just going to B, or is it A plus B plus C go to D plus E? So one reaction might be faster than the other. We really have to study the specific reaction, but the number of reacting species can certainly affect the reaction rate. Another thing that can affect the reaction rate is the physical state of the species. So are the reactants like a solid, or are they in the liquid phase? Are they in like the gas phase? Oh, this is supposed to be a gas. Or are they in the solution phase, aqueous phase? So these can all affect reaction rates because remember, reactions happen from collisions. So if there are more collisions possible, the reaction will probably happen faster. So if you have two solids that are just on top of each other, they may not react as quickly as species in solution, which can move around and hit each other more easily. Another factor affecting the reaction rate is the complexity of the reaction. So is the reaction in one step, or is it in 10 steps? The 10-step reaction might just take longer because we have to go through 10 different steps just to get to the final product. Another factor would be the order of the reaction. So if we have some reaction that says the rate equals rate constant K times A to the 0 times B to the first times C squared. So overall, this is a third order reaction, but depending on how we vary the concentration of the reactants A, B, and C, the rate will either increase or stay the same. And that actually brings me to the next factor that can affect the reaction rate, which is concentration. So in many cases, when we increase the concentration of the reactant, we are increasing the number of possible collisions, which means that there are more chances for a reaction to happen. But this is closely related to the order. So looking at this rate law I've written here, if we double the concentration of A, that's A to the 0, so the rate actually stays the same. If we double the concentration of B, that's B to the first, so the rate will also double. If we double the concentration of C, the rate will, that's C squared, so the rate will quadruple because 2 squared is 4. So the concentration can certainly affect the rate, and just as a reminder, increased concentration, I've abbreviated as CONC, means more collisions are likely or are possible because there are just more things in that small little box. Also related to that is the pressure. Now this is mostly for gas phase reactions, but for gases, the pressure is directly proportional to the concentration. And so how do we get there? Well, we start with P times V equals nRT, our good old equation, and we divide both sides by V, so we get P equals nRT divided by V. Now remember, concentration is number of moles per some volume, so here we have moles per volume. So we actually get the pressure is equal to the concentration, or molarity, times R times T. So this is how pressure is related to concentration. And again, we are increasing the chance of collisions. And so specifically, let's look at one reaction. Let's say we have 2 moles of ozone in equilibrium with 3 moles of oxygen. So if we increase the pressure, what that does is it increases the reaction with more moles in it. So the reaction with more moles is the 3 oxygens being converted to 2 ozone. So if we increase the pressure, again, I'm abbreviating pressure as press, the reaction will tend to move this way. So we'll have more ozone produced. And if we decrease the pressure, then it'll favor the forward reaction, which is ozone going to oxygen. So we'd have the reaction going this way if we decrease the pressure. Another factor that can influence the reaction rate is the choice of solvent. So solvent properties can affect reaction rates. You know, are we having a reaction that's taking place in, let's call this water, versus taking place in benzene And these are two very different solvents, and so they can affect the reaction rate very differently, or some reactions might not even happen in certain solvents. Then we get to electromagnetic radiation, or light, and the intensity of that. So radiation or light is a form of energy, and different reacting species could absorb that radiation, which would increase their energy and increase their chance of having a collision with sufficient energy to actually react. And then we have the case of some reactions, like radical reactions, where the intermediates form faster in light. So let me just draw a little picture for you. So if we have our little reacting flask and we shine light on it, that might make the reaction go faster. So another factor is a catalyst, and catalysts increase reaction rate by providing an alternative reaction pathway with a lower activation energy. So for example, if you have sucrose and you just leave it sitting there for 10 years, 100 years, even 1,000 years, and no water or anything gets on it, you'll probably just have sucrose. Just as a reminder, sucrose is just common table sugar. Now, if you put sucrose in with the enzyme sucrase, and we're just going to have this be sucrase. Sucrase is an enzyme. It's a catalyst, which means it speeds up the reaction rate without actually participating. So if we put these two together, we should end up with glucose and fructose, which are the two sugars that make up sucrose. So by itself, sucrose is probably not just going to decompose into these two, but with this enzyme catalyst, sucrose, this reaction becomes much faster. In fact, if you eat sugar, that is exactly the reaction that happens. So related to the catalyst is the surface area. So sometimes we have a catalyst that is like a piece of metal. And so if we have a piece of metal this size, only so many reactions can happen on top of the piece of metal. Now, if we increase the reaction, or we increase the piece of metal to this size, we've greatly increased the surface area, which means that the reaction can happen faster. And this brings us to our last factor that can affect reaction rates, and that is stirring. So for reactions with reactants in different physical states or different solvents, what stirring does is it simply brings those things, increases the possibility that they are going to hit each other, because now they're moving around as opposed to just staying still. So here's our little beaker, and we have a stir stick in it, and we stir it around. And then finally, for radioactive decay, which we know we can study using first-order kinetics or reaction rates. This is not really affected by any of these other factors that affect most reactions. Radioactive decay is only affected by the number of atoms in a given sample, or radioactive atoms, I should say. I should also spell atoms correctly. Number of atoms and the specific nature of the atoms, which are rate constant K for nuclear decay reactions, or lambda. Those are, again, unique to each atom. I should say that the rate constant is unique to each isotope, so they're not affected by anything else on this list, but these can all affect different types of reactions differently.